Hi everyone. In this lesson, we're going to cover the addition rule for computing probabilities and look at a few examples. Now down here we have stated our general rule of addition for computing probabilities, and it states that the probability of event A or event B occurring is equal to the probability of event A occurring plus the probability of event B occurring minus the probability of event A and B both occurring at the same time. Now as we look through some of our examples, you'll get a better understanding of why this rule holds, along with why we have to subtract off the probability of A and B occurring at the same time from these two probabilities. Now in the case when the events A and B are mutually exclusive, then the probability of A and B is equal to 0. Recall, mutually exclusive means that they cannot both occur at the same time, so of course the probability that they do both occur at the same time is 0. In which case then the general rule of addition becomes our special rule of addition that we have stated right here. So you see, if this term right here is equal to 0, well, then of course we just have probability of A plus probability of B, which is what we have listed down here. Now I recommend that you just use the general rule of addition when you're working on problems, because if A and B are mutually exclusive, you'll see that in the problem and you'll set this term equal to 0 and then you'll get the correct answer. But if you use the special rule of addition and the probability of A and B is not equal to 0, well, then you'll get the wrong answer. So I recommend always using the general rule of addition. Now let's take a look at a few examples. So in this example, we have a card is drawn at random from a standard 52 card deck. And for part A, we want to find the probability of drawing an ace or a 10. And then we want to find the probability of drawing a 10 or a diamond, indicated like this. So first of all, note this before we start the problem. In a standard deck of cards, you have 4 aces, 4 tens, and 13 diamonds. So take note of that first. So for part A then, the probability of an ace or a 10 is going to be the probability of an ace plus the probability of a 10 minus the probability of an ace and a 10. That's following our addition rule. You see the ace is like the event A and the 10 is like the event B, thinking back to our addition rule, and then we have A and B right here. Now the probability of drawing an ace is 4 over 52. Probability of drawing a 10 is 4 over 52 as well. And the probability of an ace and a 10, well, those events are mutually exclusive. You can't have a card that is both an ace and a 10. So this is equal to 0. And you get our answer of 8 divided by 52, which is approximately 0.15 or a 15% chance. So notice how in this case we actually ended up with the special rule of addition because our events were mutually exclusive. But we applied the general rule at first and we saw that this term was equal to 0, so we just put a 0 right here. So that's why I recommend that you just use the general rule of addition. Now also note this. You could actually do this problem without using the addition rule if you just think about how a deck of cards is structured, and that'll give you a better understanding of why the addition rule works. For example, if you think back to a deck of cards, right here we have pictured a deck of cards. So right here's our deck of cards, and we wanted to find the probability of drawing an ace or a 10, so of course we have 4 aces and 4 tens. So obviously the answer is going to be 8 over 52. And notice how we had to add these two numbers. So that's why we call it the addition rule. Now let's take a look at part B. Now for part B, we want to find the probability of a 10 or a diamond. So we apply the addition rule again. So that's going to be the probability of a 10 plus the probability of a diamond minus the probability of a 10 and a diamond. So the probability of a 10 is 4 over 52 because there are 4 10s in a deck of cards. The probability of a diamond is 13 over 52 because there are 13 diamonds in a deck of cards. And then we have to subtract off the probability of a 10 and a diamond. Well, that basically just means the probability of getting a 10 of diamonds. And there's only one card in the deck that has this property that is both a 10 and a diamond. It's the 10 of diamonds. And so your probability for this part is going to be 1 over 52. So our answer is 4 over 52 plus 13 over 52 minus 1 over 52, and we get 16 over 52, or approximately 0.31. And that's our probability, or 31% chance. Now, think back to the deck of cards and how it's structured. This will give you a good understanding of why we have to subtract off this probability of 10 and a diamond. So if you go back to our deck of card picture, you see we wanted to find the probability of drawing a 10 or a diamond. Well, there are 4 10s and 13 diamonds. So you see, if you add 4 over 52 plus 13 over 52, you see what you've done by adding these together is you've repeated this 10 of diamonds twice, because you've added it up going down this column and you added it going across the bottom row here. So this is included twice. So you see you actually have to subtract it off. So you have to subtract off 1 over 52, and that gives you your probability of 16 over 52. Or you can also think, well, how many 10s and diamonds do I have in the deck of cards? I have 4 10s, 13 diamonds. But when you add these together, you've repeated this twice, so you have to subtract it off, and you get 16 total cards that satisfy the criteria of being a 10 or a diamond, and you get your probability of 16 over 52. So this example gives you a good understanding of why we have to subtract off the probability of A and B. Because the probability of A and B is contained in each of these two terms. So the probability of 10 of diamonds is contained in both of them, so we have to subtract off one of them. Now let's consider this example. So here we have a 12-sided die with the numbers 1 through 12 on the faces, and we want to find the probability of rolling an even number or a number greater than or equal to 9. Notice the or right here. So to solve this problem, we're going to apply the addition rule. Now let's let the event A be the event of rolling an even number, so this is going to be A. And let's let B be the event of getting a number bigger than or equal to 9. So you notice A can occur by getting either a 2, 4, 6, 8, 10, or 12. And B can occur by getting a 9, 10, 11, or 12. Also notice that A and B can occur by getting either a 10 or a 12. So they're not mutually exclusive events in this case. You can roll a die and event A and B can both occur at the same time if we get a 10 or a 12. Notice the 10 and 12 are in both of these sets. So then by the addition rule, what we have is this. The probability of A or B is going to be probability of A. Now, that's going to be 6 out of 12 because we have 6 numbers in here. So 6 over 12 plus the probability of B. Now that's going to be 4 over 12 because we have 4 numbers in the B set, minus the probability of A and B, which is going to be 2 over 12 because we have 2 numbers in the A and B set. And when we add these terms together, we get 8 over 12, which is our answer. Now notice once again that you could have just sort of done this problem in your head without the use of the addition rule. If you think about how can A or B occur? Well, you see down here we have listed A or B is actually this entire set of numbers right here. A or B can occur by getting either a 2, 4, 6, 8, 9, 10, 11, or 12. And there are 8 numbers in here. So the probability of A or B is 8 over 12. You could have just counted that up in your head if you wanted to. But also notice that in the addition rule here, notice how the probability of A has a 10 or 12 in it, and the probability of B also has a 10 or a 12 in it. And so you see the 10 and 12 is repeated in each of these. So once again, that's why we had to subtract off one of them. And so that illustrates again why we have to subtract off the probability of A and B one time when we apply the addition rule. Here we have another example. So in this example, we have a Venn diagram that illustrates the results of a survey of tourists who visited Florida during the year. The survey revealed that 60% went to Disney World, 50% went to Busch Gardens, and 30% visited both. Now this here is called a Venn diagram. It illustrates graphically the problem situation. You'll see these used a lot to illustrate probability topics and concepts. In this Venn diagram, the area of the rectangle here is 1, the total area. And the area of each circle represents a probability. So the area of this circle is 0.6, representing the probability that a randomly selected person went to Disney. The area of this circle is 0.5, representing the probability of the person having gone to Busch Gardens. And the intersection is 0.3. The area of the intersecting region is 0.3, and that represents the probability that a randomly selected person visited both Disney and Busch Gardens. So that's how you read a Venn diagram. Now we have this question to answer. What is the probability that a randomly selected person from the survey group visited either Disney World or Busch Gardens? So we just have to apply the addition rule here. Probability of Disney or Busch Gardens is probability of having visited Disney plus probability of Busch Gardens minus the probability of visiting Disney and Busch Gardens. And we simply enter our data that we have up here into this equation on the right hand side. So probability of Disney is 0.6, Busch Gardens is 0.5, and then we have to subtract off the probability of having visited both, which is 0.3, and we end up with 0.8. And that's our answer. It's as simple as that. And if we consider this Venn diagram up here, we can also obtain the answer of 0.8. Sometimes looking at a problem graphically gives you a little better intuition into the problem solution. So you notice the area of the larger circle is 0.6. The area of the intersecting region here is 0.3. So the area outside of this intersecting region and still inside the big circle must be 0.3. So this area is 0.3. The area of the intersecting region we know is 0.3 as well. And the area of the smaller circle is 0.5. And so the area of this region that's inside the smaller circle but outside the intersecting region must be 0.2. So if we add all of these together, we get the area of this entire circle, this entire region here. And that area represents the probability of visiting Disney or Busch Gardens. And so you see we get 0.3 plus 0.3 plus 0.2. And that gives us 0.8, which is what we found down here using the addition rule. So sometimes looking at a problem graphically can give you a little better intuition into the solution of the problem. Let's take a look at an example involving contingency tables. Now here's an example of how to use the addition rule with contingency tables. So for this example, researchers in Pennsylvania asked students in grades 4 through 6 in 3 school districts about what they thought was the most important thing in school: making good grades, being popular, or excelling in sports. There were rural, suburban, and urban schools surveyed, and the table below lists the results. So here's our question. If one of the students is selected at random, what is the probability that they thought grades were most important or came from an urban school? So in this case, we're going to let the event A be thinking that grades were most important. So that's our event A. And coming from an urban school is our event B. And we have an OR in between them. So we see that we want to apply the addition rule. So down here, probability of grades being most important or being from an urban school is going to equal probability of grades plus probability of urban minus the probability of thinking grades are most important and being from an urban school district. Now, to calculate these probabilities here, probability of grades, we need to sum all of the values in the grades row, which we have in this rectangle right here. Now these numbers sum to 255 that we have over here in the totals column. And we have a total number of students who were surveyed being 493. So the probability of randomly selecting a student who thinks grades are most important would be 255 out of 493, which we have right here. Then the probability of randomly selecting a student and having them be from an urban school district, well, if we sum up all of these entries, that's 181, and so this probability is going to be 181 out of 493. Then we have to subtract off probability of being from an urban school district and thinking that grades are most important. Well, that's this entry right here, which is included in both rectangles. And so that probability is going to be 103 out of 493. Adding these results up, we get 333 over 493, or 0.68, or a 68% chance of selecting a student and having them either come from an urban school or feeling that grades are most important. Now notice we could have also obtained this probability just by adding up the numbers 60 plus 92 plus 103 plus 52 plus 26, just adding those numbers up, and you would still get 333. And also keep in mind here, you see why we have to subtract off this 103 right here when we apply the addition rule once again, because in this 255 right here, the 103 is already included in the 255, and in the 181 it is also included in this number. And so the 103 is included both in the 255 and the 181, so we have to subtract off one of the 103s, and that's what we do right here. That's why we subtract the probability of grades and urban, and we obtain our result. So once again, you see why we have to do that subtraction. And that concludes our discussion about the addition rule.